Welcome to our comprehensive journey through thermodynamics. In this chapter, we'll unravel the fundamental laws that govern energy, heat, and work in the universe. Thermodynamics is not just a branch of physics. It's a powerful tool that helps us understand everything from engines to refrigerators, and even the weather. As we move through each concept, you'll see how these principles apply to real-world situations and why they are essential for engineers, scientists, and anyone curious about how the world works. Let's begin by exploring the foundational laws that set the stage for all thermodynamic processes. Zeroth law of thermodynamics might sound simple, but it's crucial for everything that follows. It states, if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. This law forms the basis for the concept of temperature. Imagine 3 cups of water. If cup A is as warm as cup B, and cup B is as warm as cup C, then cup A and cup C must be at the same temperature. This seemingly obvious statement allows us to measure and compare temperatures in a meaningful way. Temperature is a fundamental property that arises directly from the zeroth law of thermodynamics. According to this law, temperature is the property that determines whether or not two systems are in thermal equilibrium. In other words, if two objects have the same temperature, no heat flows between them when they are in contact. This definition allows us to use thermometers and other devices to measure temperature accurately, providing a consistent scale for scientific and everyday use. First law of thermodynamics is all about the conservation of energy. It states that energy cannot be created or destroyed, only transformed from one form to another. In thermodynamics, this means the change in internal energy of a system equals the heat added to the system minus the work done by the system. This principle is the foundation for understanding how engines, refrigerators, and even our bodies manage energy. It ensures that every bit of energy is accounted for, no matter how it changes form. Let's dive into how work is done during an isothermal process, where the temperature remains constant. In such a process, any heat added to the system is used entirely to do work, since the internal energy doesn't change. The work done by an ideal gas during isothermal expansion or compression can be derived using the ideal gas law and integrating pressure over volume. This relationship is key for understanding how engines and other devices operate under constant temperature conditions. Now, let's look at adiabatic processes, where no heat is exchanged with the surroundings. In an adiabatic process, all the work done results in a change in the internal energy of the system. This is different from isothermal processes, where heat can flow in or out. The mathematical expression for work in adiabatic processes involves the specific heat capacities and the change in volume. Understanding this helps explain phenomena like the rapid cooling of gases when they expand quickly. Specific heat capacity at constant volume, often denoted as CV, is the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius while keeping the volume constant. This property is crucial for understanding how substances absorb and store energy. In real-world applications, CV helps engineers design systems where volume doesn't change, such as sealed containers or certain engine components. Specific heat capacity at constant pressure, or CP, is the heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius at constant pressure. CP is especially important in processes where pressure remains unchanged, such as atmospheric heating or many chemical reactions. Knowing CP allows scientists and engineers to predict how much energy is needed to heat substances in open systems. There's an important relationship between the specific heat capacities at constant pressure, CP, and constant volume, CV. For ideal gases, CP is always greater than CV because, at constant pressure, some energy goes into doing work as the gas expands. The difference between CP and CV is equal to the universal gas constant. This relationship is fundamental in thermodynamics and helps in calculating energy changes in various processes. Second law of thermodynamics introduces the concept of irreversibility in natural processes. It states that heat cannot spontaneously flow from a colder body to a hotter body. This law explains why certain processes, like mixing hot and cold water, only happen in one direction. It also lays the foundation for understanding efficiency limits in engines and refrigerators and introduces the concept of entropy, a measure of disorder in a system. Kelvin-Planck's statement is one way to express the second law of thermodynamics. It says, no heat engine can convert all the heat it absorbs into work. Some energy must always be expelled as waste heat. This principle sets a fundamental limit on the efficiency of all engines. No matter how well designed, every engine must lose some energy to its surroundings, making 100% efficiency impossible. Clausius' statement is another way to express the second law of thermodynamics. It states, heat cannot spontaneously flow from a colder object to a hotter object without external work being done. This is why refrigerators and air conditioners require energy input to move heat from a cool space to a warm one. The Clausius statement reinforces the idea that natural processes have a preferred direction. Heat engine is a device that converts heat energy into mechanical work. It operates by taking in heat from a high-temperature source, converting part of that energy into work, and releasing the remaining heat to a low-temperature sink. Examples include car engines, steam turbines, and even power plants. Heat engines are central to modern technology, powering vehicles, factories, and electricity generation. Efficiency of a heat engine is a measure of how well it converts heat into work. It's defined as the ratio of work output to heat input. No engine can be 100% efficient due to the second law of thermodynamics. Some energy is always lost as waste heat. Understanding efficiency helps engineers design better engines and reduce energy losses in practical applications. Carnot engine is a theoretical model that represents the most efficient heat engine possible. It operates in a reversible cycle between two temperature reservoirs. The Carnot engine sets the upper limit for efficiency that any real engine can achieve. While no real engine can match the Carnot engine's efficiency, it serves as a benchmark for evaluating and improving practical engines. Efficiency of a Carnot engine depends only on the temperatures of the hot and cold reservoirs. It's given by the formula. Efficiency equals 1 Tc/Th, where Tc is the cold reservoir temperature and Th is the hot reservoir temperature, both in Kelvin. This formula shows that higher efficiency is possible only with a larger temperature difference. The Carnot efficiency is the theoretical maximum for any engine. Entropy is a central concept in thermodynamics, representing the degree of disorder or randomness in a system. As processes occur, entropy tends to increase, reflecting the natural tendency for systems to move towards greater disorder. Entropy helps explain why certain processes are irreversible and why energy becomes less useful over time. It's a key factor in understanding the direction of natural processes. Increase of entropy principle states that in any natural process, the total entropy of a system and its surroundings always increases or remains the same. This principle explains why some processes are irreversible and why perpetual motion machines are impossible. It also underpins the concept of the arrow of time, showing that time naturally moves forward as entropy increases. Refrigerator is a device that moves heat from a cold space to a warm space using external energy. It works by absorbing heat from the inside of the fridge and releasing it to the room outside. This process is the opposite of a heat engine and requires work to be done, as dictated by the second law of thermodynamics. Refrigerators are essential for preserving food and keeping our homes comfortable. Coefficient of performance, COP, is a measure of a refrigerator's efficiency. It's defined as the ratio of heat removed from the cold space to the work input required. A higher COP means the refrigerator is more efficient, using less energy to move the same amount of heat. Understanding COP helps in designing more energy-efficient cooling systems for homes and industries. Thermodynamics isn't just theoretical, it's everywhere in our daily lives. From the engines that power our cars to the refrigerators that keep our food fresh, thermodynamic principles are at work. Understanding these concepts helps us design better machines, save energy, and even tackle global challenges like climate change. The study of thermodynamics is essential for innovation and progress in technology and society. Thermodynamic system is any part of the universe we choose to study, separated by boundaries from its surroundings. Systems can be open, closed, or isolated, depending on whether they exchange matter or energy with their environment. Understanding the type of system is crucial for analyzing energy flows and predicting how processes will unfold. Open systems can exchange both energy and matter with their surroundings, like a boiling pot of water. Closed systems exchange only energy, not matter, such as a sealed steam radiator. Isolated systems exchange neither energy nor matter, like a perfectly insulated thermos. Identifying the system type helps in applying the correct thermodynamic laws and equations. In thermodynamics, state functions are properties that depend only on the current state of the system, not on how it got there. Examples include temperature, pressure, and internal energy. Path functions, like work and heat, depend on the specific process taken. Distinguishing between these helps clarify calculations and predictions in thermodynamic analysis. Internal energy is the total energy contained within a system, including both kinetic and potential energy of its particles. Changes in internal energy are central to the first law of thermodynamics. By tracking internal energy, we can understand how heat and work interact during various processes, from chemical reactions to engine cycles. Heat and work are two ways energy can be transferred between a system and its surroundings. Heat is energy transferred due to temperature difference, while work is energy transferred due to force acting over a distance. Both are path functions, meaning their values depend on the process taken. Understanding these concepts is key to mastering thermodynamics. Thermodynamic processes describe how a system changes from one state to another. Common types include isothermal, constant temperature, adiabatic, no heat exchange, isobaric, constant pressure, and isochoric, constant volume processes. Each process has unique characteristics and equations, making them essential for analyzing real-world systems. An isothermal process occurs at a constant temperature. During this process, any heat added to the system is used to do work, and the internal energy remains unchanged. Isothermal processes are important in understanding how gases behave under controlled temperature conditions, such as in certain laboratory experiments and industrial applications. In an adiabatic process, the system does not exchange heat with its surroundings. All energy transfer occurs as work, leading to changes in internal energy and temperature. Adiabatic processes are common in rapid expansions or compressions, such as in piston engines or atmospheric phenomena like rising air parcels. An isobaric process occurs at constant pressure. In this process, the heat added to the system goes into changing both the internal energy and doing work as the system expands or contracts. Isobaric processes are common in everyday life, such as boiling water at atmospheric pressure. An isochoric process, also known as an isometric or constant volume process, occurs when the volume of the system remains unchanged. In this case, any heat added changes only the internal energy, as no work is done. Isochoric processes are important in understanding how gases behave in rigid containers. Reversible processes are idealized changes that can be undone without leaving any trace on the surroundings. In reality, most processes are irreversible, meaning they increase the total entropy of the universe. Understanding the difference helps in analyzing real systems and improving efficiency. A thermodynamic cycle is a series of processes that return a system to its original state. The most famous example is the Carnot cycle, but real engines use cycles like the Otto or diesel cycle. Analyzing cycles helps us understand how engines and refrigerators operate over repeated use. The Otto cycle is the basis for gasoline engines, while the diesel cycle powers diesel engines. Both cycles involve a series of thermodynamic processes, including compression, combustion, and expansion. Understanding these cycles helps engineers optimize engine performance and fuel efficiency. Heat pumps are devices that transfer heat from a colder area to a warmer one, similar to refrigerators, but often used for heating buildings. They use external energy to move heat against its natural direction. Heat pumps are becoming increasingly important for energy-efficient heating and cooling solutions. While ideal engines like the Carnot engine provide a benchmark for efficiency, real engines always fall short due to friction, heat loss, and other irreversibilities. Engineers strive to minimize these losses, but some inefficiency is unavoidable. Comparing real and ideal engines helps identify areas for improvement. Thermodynamics is at the heart of power generation. Power plants use heat engines to convert fuel into electricity, following thermodynamic cycles. Improving efficiency in these plants can save resources and reduce environmental impact, making thermodynamics crucial for sustainable energy solutions. Refrigerators and air conditioners rely on thermodynamic cycles to move heat from cool spaces to warmer ones. By understanding these cycles, engineers can design more efficient cooling systems, reducing energy consumption and environmental impact. Natural processes, from weather patterns to biological functions, are governed by thermodynamic principles. For example, the water cycle and the way animals regulate body temperature both rely on energy transfer and entropy changes. Studying thermodynamics helps us understand and predict natural phenomena. Thermodynamics plays a vital role in understanding climate change. The flow of energy in Earth's atmosphere, the greenhouse effect, and the efficiency of energy use all relate to thermodynamic principles. By applying these concepts, scientists can model climate systems and develop strategies to mitigate global warming. Engineers use thermodynamics to design everything from engines to HVAC systems. By understanding energy flows and efficiency limits, they can create safer, more reliable, and more efficient machines. Thermodynamics is a cornerstone of mechanical, chemical, and even electrical engineering. From boiling water for tea to using air conditioners in summer, thermodynamics is at play in countless daily activities. Understanding these principles can help us make smarter choices about energy use, saving money and reducing our environmental footprint. Innovations in energy technology, from solar panels to electric vehicles, rely on thermodynamic principles. By pushing the boundaries of efficiency and sustainability, thermodynamics drives progress in renewable energy and green technology. We've covered the essential laws and concepts of thermodynamics, from the zeroth law to entropy and real-world applications. These principles form the backbone of modern science and engineering, shaping the way we understand and interact with the world. Mastering thermodynamics opens the door to countless opportunities in technology, research, and daily life. As we move forward, keep these thermodynamic principles in mind. Whether you're studying advanced physics, engineering, or simply curious about how things work, thermodynamics will continue to be a guiding force. Stay curious, keep exploring, and remember, the laws of thermodynamics are always at work, shaping our universe every moment.